My name is Claes. I'm a developer at Cisco, working on NSO and have been so for the past 8 years. And as John mentioned, I'm going to talk about our new backend updates that was released in NSO 6.4. So, problem statement, NSO is consuming a lot of memory. If you have a larger installation, you probably have experienced this yourself already, where your NSO processes is taking too much memory and you need to get larger and larger servers. So in order for us to improve this, we needed to get a good picture of what is consuming memory to begin with. So our main picks was CDB. There we have the device data and the service data. This obviously grows the more devices you manage, the more device data you get, the more service instances you have, the more service data you have. Then we have schema. So if you have a network with a lot of different devices, you will have a lot of nets. The nets have large models, so the schema data will grow. And on business systems, your transactions will consume quite a bit of memory too, because we track everything you write, obviously, but we also track whatever you read in order for us to have an optimistic concurrency model. And then we have the Java and Python VMs. They too consume memory of themselves, but they also load the schema data from NSO, so that also adds up quite a bit on the memory consumption. So with those assumptions, we took a look at a few different installations and to verify that we're actually correct. And here you have one of those installations with proper real-world data. And 2/3 of the data is device data. And the rest of that is basically split. 50% of that is service data. And then we have a tad bit of Python VM, Java VM, and the schema data. The transactions is very momentarily taken. It depends on a specific point in time. So it's going to fluctuate a lot. The other parts are quite static. So given that most of the data resides in CDB from our measurements, we decided to take a closer look at that. And for us to improve it, we need to understand what it is first. So CDB is an in-memory tree database, which is good because we are typically accessing and modifying trees of data. Yang models can be represented as XML documents, which is basically a configuration tree. And it being an in-memory tree, it provides for a very low read overhead. Everything is available in memory at all times. We don't need to go to a disk to read stuff. And it's backed by a single journal file, which gives a benefit of having a low write overhead, because we are just appending to a log of operations where every transaction gets a new section in the file, and appending to a file is cheap, so it's fast. However, this file will continuously grow for each new transaction in it. And at some point, you will want to shrink that file. And for us to do that, we need to compact it, meaning we will write a new transaction with all the current data in it. And due to this journal file layout, we require all data to be loaded at startup, because it's just a sequence of transactions and it's the sum that represents the current state. So if you would load half of it, you would be at the correct state from the past, but not the current state. And it's not structured in any way, shape, or form. So you could load parts of the tree. So This is why we need to load all data at startup. So with all this, we sat down and thought a bit and figured we could probably improve this by introducing a new backend while retaining a lot of the current properties and code. So we now have an in-memory tree database as before. So if data is in the memory tree, and we still have this same low read overhead because it's the same data tree. However, we now also want to load data on demand so that you don't have to load it at startup. We can start basically an empty tree, and whenever you start reading, we will load that data in. But we don't want it to continuously grow the more you use it. So we also have offloading of the data loaded into the tree. And then for us to do this, we have it backed up by a disk storage layer. This is implemented using RocksDB, which is a key value storage developed by Meta. And it requires no additional database process or setup or installation. It's a library which is loaded into NSO. So there's no additional setup for you end users. So on a very high level, this is what it looks like. We have CDB, and whenever CDB wants to provide data to a part of the system, it reads from the in-memory tree. If it's in the in-memory tree, that data will be just returned to CDB as usual. If it's not, the in-memory tree will query the disk storage, and if the data is available, it will return that to CDB. At the same time, loading of related data will be initiated to speed up subsequent read requests. And when we are writing directly to the disk storage using transaction to that device or device storage, not to the memory tree. However, when we commit data to the disk storage, and that includes all change data. But we also update the in-memory trees. So if the transaction contains data that has been loaded by the in-memory tree, that data is updated. If we're deleting data that's loaded in the in-memory tree, that data is removed. However, we do not load data in as we commit it. So if you commit a large piece of data, that will be on disk, but it won't be updated in memory. It will be so whenever you access it later on. That's getting data into memory. To get it out from memory, we support offloading select parts of data tree. We call these offload points. We only track certain parts of the tree to reduce the overhead of the tracking. And as was shown in the pie chart earlier, it's basically device data and service data that consumes most of the data in an NSO system. So that's what we track. So by default, device config is an offload point. So for each device, it will track the config subtree for it. And whenever you load packages in with service points, those will be added as well. We have two ways of specifying when we want to offload things. And one is a max memory limit. The default is set to 50% of available system memory. And when the memory consumption go above that the CDB memory consumption, that is, goes above that threshold, we start offloading the oldest data. And that's then looking at when the above mentioned offload points was last accessed, and we're picking the oldest ones from there, and we offload. And we keep on offloading until we are below the threshold. If we fail to come below the threshold while offloading, we do raise an alarm, because that basically means we have enough data in CDB that's outside the device tree and the service points to fit your given limit, and your system will behave and perform poorly, because whenever you access device or service data, they will be immediately offloaded. We also have age-based offloading, so if you access some things very seldom, you might want to free up resources for other things by just looking at when it was last accessed and then offload it preemptively. All the offloading is done periodically. So if you have a certain memory limit, it doesn't mean we will never go above that limit. It means NSO will check if we are above that limit at given intervals, and if we are, we will trigger the offloading. The default offloading interval is every 5 seconds, and the age-based offloading is disabled. So when we got all these changes in, of course, we needed to measure to see that what we have done gives us the expected results. And here are some of the results we've gotten so far. First off, startup time. Here we are using a use case from the CNC suite with provisioning of devices. And here the startup time went down from almost 18 minutes down to a bit more than 6, which is a major improvement. However, it's still quite a long time, 6 minutes, but a majority of that time is spent loading the schema of NSO. In another undisclosed use case, it's actually slower to start with the disk storage backend. This is because CDB is rather small, and we get some overhead of incrementally loading data in and initializing RocksDB itself. And then we have the measurements on the same provisioning service. This is on a system with 10K services in CDB already provisioned. And here we see quite good improvements or on par performance across the board. So if we're creating a new service instance here, it's 3 times as fast, which is surprising, but also very good. Cold updates perform on par. Cold meaning that the service data is not yet in memory. And an hot update is actually faster. Hot deletes are actually faster, and the cold deletes are faster. And then hot deletes are equally performant as the old one. This gets even more evident when we do large scale tests, creating 10K services in a go. Mind you, these services have quite small transactions. There's a large amount of transactions, but each one of them does not commit much data. And here we basically see 3-time improvement on create and update, and delete. It's a bit faster than twice as much. This is not numbers you should expect from every use case. This is very use case specific. If your service is writing a lot of data in one go, or deletes large chunks of the tree at the same time, etc., you won't be seeing these numbers. The larger transactions, the more overhead we get off the other backend. But for some use cases, it shows really good improvements. But it's not all rainbows and butterflies. Loading data comes with some overhead. Two main use cases for this becomes really evident is creating rollback files and performing sync froms, where when we create a rollback file, we want to create a file that contains all the data that was in the system before the current transaction goes in. So if you're deleting a large part of your configuration in a transaction, that requires all that data to be available in the rollback file. And if we haven't loaded that into the memory yet, we will have to, so that during the rollback file creation, which shows in performance numbers, because it's incrementally loaded while we are creating the rollback file. Sync from is another example of this, where for us to do a sync from, we fetch the full configuration from the device, and then we need to compare that with everything that's in CDB. So if you don't have any of that device's data in memory, and it's a large device, we will have to load that full device into memory incrementally. And that shows, it's evident. You will notice that in your performance numbers. Another example of the same kind of thing is if you do a netconf request, resconf get or similar, where you want to load a large chunk of the configuration, you will see a major slowdown in doing so. But on average, the penalty of loading data seems to be around 2 to 10%, depending on use case. And worst case is 150%. So it can be quite bad in some scenarios. However, as shown before, in a lot of instances, this overhead is not where you're going to spend the majority of time executing. To show a bit about how the offloading behaves, here's a graph, two graphs from a system running tests. We have a lot of services and devices created in NSO, where the services update n amount of devices. For instance, there's no overlap in them, so we don't have to worry about conflicts or anything like that. And we see the graph from start, where it's a bit more than 100 megs of data loaded. And then the tests start doing random update of services at a very rapid rate. We're doing around 60 updates per second here. And we see that data gets loaded in up during the first 10 minutes of execution. And at that point, we see at the lower graphs, we see that we start offloading data. Worth mentioning here is that we have a 1 second offloading interval. If that interval would have been higher, the above graph where we see the CDB size would be moving more up and down, because we would, let's say it was 10 seconds or 50 seconds, we would allow the memory to go above that threshold during that interval. And when we then check, we would ensure we would continue to offload until we get below it. But now we check every second, so basically we are offloading and loading as fast as we can. And we see then in the below graph, we are offloading devices. One is devices and one is service points concurrently. a number of offload points being required for us to become a state where we're below. The limit depends on how large they are, because we offload data in its entirety. So when we are above the threshold, we find offload points. We offload all data under device config for that device, or all data under the service for that service we are offloading. And then what does this have for what does it mean for you as a NSO user? How does this affect the way you use NSO? First off, it should allow you to manage larger networks per NSO node, because we don't have to have all data in memory at all times. So when you now size a server, you don't need to limit it by the amount of available RAM. Previously, there were a strong correlation between number of devices managed and the available memory on the server. Now, that was one of the major factors. And the other factor was how much work was that node going to do. So now, on the other hand, you will still need to focus on how many transactions you're going to process in a given time span and how expensive they are. So, but if you have a really large network with a lot of devices, but they don't get updated too frequently, you should be able to run with a much leaner machine, because even though there might be some overhead of loading the data in, potentially making your transactions a bit slower, there's still enough headroom in the server capacity to manage that, but you will never run out of memory as before. Another thing that will impact the way you run NSO is the fact that the compactions no longer cause service interruptions. RocksDB will reclaim disk space in the background as it runs, so there's no need to run any explicit or having the automatic compaction run at an inappropriate point in time. And then some questions that's been popping up as soon as this has been brought up. And first off, if it's backwards compatible. As I tried to explain earlier, it's still using the same in-memory tree. So it's backwards compatible from a functional perspective internally in NSO and also externally. There are changes on how data is stored on disk. So the disk files are, of course, not interchangeable. And if you're doing system maintenance or administration, the backup files or the way you back up will change, because previously you had a single file per data store. Now you have a directory with multiple files in it. So it is backwards compatible, but there are some caveats on how you manage a system. And yes, it does require migration. As I mentioned before, the on-disk format is completely different. However, the migration is automatic. You update the configuration in your NCS conf, you restart, and then when NSO starts, it'll notice that the on-disk files do not correspond to what's in the configuration, and we'll start an automatic migration to the new format. The migration is logged in NSS log, and there's also progress logs log to the devel log if you are migrating a large data store, because then it will take quite some time. Do keep in mind when you do these migrations that there's enough disk space on the server available. Typically, RocksDB, the new format, takes a bit more than the CDB files, but not too much. Let's say add a 10% to what you have used for a compacted CDB store. If it's not compacted, it's basically impossible to tell because it doesn't represent what's in the memory tree in its entirety. Yes. And yes, you can use it. Don't mention it. It's been released in NSO 6.4. So you just can change your NCS conf and you try it out. However, it's worth mentioning we are still working on improving performance on this, and for 6.4.1 there's improvements coming for data loading in parallel workloads. So if you have a highly concurrent use case, you might see improvements coming already in the next release. And that was all for me.
Hey, great session, Claes. This is a big development in the world of NSO. One of the bigger things we've done over the years, so it's exciting. We do have a couple of questions from the audience. One is kind of related to, you already covered, migration, but can you migrate back and forth between the data stores? Say, once you migrate to the new backend, can you migrate back to the old backend if you so wish? What is that choice?
Yes, you can. It's the short answer. But if I elaborate a bit, so what happens when we migrate back to a new format? A backup will be created of these old files. So you have the current state from when you just started your journey on the new format available. That will be logged in your NCS log on startup and will warn you. It's like, hey, there's a lot of data here. You probably would want to move this elsewhere because it's using up a lot of disk space. But if you, for whatever reason, figure you need to go back to the old format, you just change your NCS conf back. There's a new persistence check section under CDB. You change that back and use restart NSO. It will figure out, hey, the old format is what's requested. There's the new format disk files on disk, and it will migrate it back to the old format, and then you can go on with life. So there's a safety net there too.
Okay, so people can experiment to their heart's content in the lab, taking this back and forth and understanding it. Have kind of an interesting deep question here from a customer. So say someone does an XPath query of just //star, kind of, this is the equivalent of the disk system RM/. What so that query, could theoretically try and load all the CDB into memory. If it exceeds the max memory limit and potentially even memory available in the server, what's the expected behavior?
Compared to running with the old backend, it's going to run slower if not everything is in memory already, because we incrementally load it in. So that's one difference, because we get the loading overhead. And depending on how you're outputting that, it's going to come with the outputting process of the result is probably going to be slower than the loading and offloading counterparts. So you're hopefully going to load or output data loaded in at a pace that's slow enough for NSO to be able to offload it in time. So it will load and offload data at the same time. It won't wait until the query is done before it starts offloading. So depending on your offloading interval and how high the threshold is set, it might just go fine, but slower. Or if it's a lot of data and a really small system, it might run out of memory. Yes.
Okay, sounds good. And I'm assuming best practice here is that people should migrate the back end on its own. Don't do any data model updates, package updates, or anything is part of the same operation as best practice. So is that correct?
Yes, I'd highly recommend you do the upgrade initially so that if you find any issues, it's because of the backend change or it's because of other changes in NSO or your services.
Okay, great, Claes. So with that, we'll wrap up your session. Thanks for giving this great look into this major new development in NSO.